confused when we start. Okay. So if we look at just this dot product now, if V1 and V3 are orthogonal, what about V1 dot 2 times V3? Well, we have a product of dot products. It says if I throw in a scalar like that, I can multiply the scalar there, or I can kind of factor out that scalar and write that as this thing. But if V1 and V3 are orthogonal, then what's this dot product? 0. What's 2 times 0? 0. So this thing is still equal to 0. So they are orthogonal. So scaling doesn't change the fact that they're orthogonal. Well, that's kind of nice because I might not want to double them, but I might want to do this. I might want to divide them by some number, a specific number, for instance, maybe the magnitude of each of these vectors. And why would I want to do that? Absolutely. Now I have an orthonormal basis, right, which is a little better. It's one step better, right? We orthogonalize to get that nice orthogonal basis, and now we can normalize this set to make them an orthonormal basis, or sometimes we'll write as this, orthonormal basis. All right, we'll just shortcut that. And we can see there's still a basis, they're still orthogonal. Any questions about that at all? Okay. So our plan for today is to look at one kind of more general example of Gram-Schmidt. After that, I'll open up to questions if you guys have any questions about anything so far. And then we'll move on to talking about orthogonal matrices and the QR factorization. Hopefully at the end we'll have a little time to talk about approximation using the projection. That's our plan for today. All right, more example case of Gram-Schmidt. We've been talking about now that vectors can mean more than just vectors. A vector space can be a more general thing. And so we've used some of these examples before. So for instance, I could call V my set of polynomials. In fact, this is the set of all second-degree polynomials. And I could have a basis for this set. So if I have a basis for this set, 1x squared, is that a basis for this space? Does it make sense that would be a basis? Let me justify why that's a basis for me. What does a basis need to be? What's a basis? What's the definition of a basis?
Literally independent set of vectors that span the space.
Absolutely. So I have three vectors here, the vector 1, the vector x, the vector x squared. Are they linearly independent? They seem to be. Right, is there any way I can take 1 and x and somehow add them or add multiples to get to x squared? Can I take one of these plus 3 of these and somehow get to x squared? I can't, right? I don't combine polynomials that way. Is there any way I can take 3x squared, minus 10x and somehow get just 1? I can't, right? So these are clearly linearly independent then. So they're not linear combinations of each other. And can I get to any second degree polynomial using some combination of these? If I wanted to get to this one, can I take a linear combination of these vectors to get to there? Sure, I'll take 3 of this one and minus 4 of this one. All right, so I can use these to generate all second degree polynomials. So this is a basis for this vector space. Of course, really formally, I should first show that it is a vector space, but I think we've talked about that one before. Then next, I'm adding an inner product to my vector space. I'm turning it into an inner product space or a Hilbert space. And this is how I'm defining my inner product. I'm taking two elements from the vector space, a u and a v, and I'm integrating their product from 0 to 1. I kind of hinted that we could do that as well earlier. Now, of course, once I define this, I should really show that it's an inner product. I should show that it satisfies those 4 properties that we talked about earlier. And I could do that. But assuming it is an inner product space, and I have this basis, I want an orthonormal, or in this case, I want an orthogonal basis for this vector space. So I can use Gram-Schmidt just like I did before. I have a U1, a U2, and a U3, and I want to turn it into a V1, a V2, and a V3. So how do I start? What's my V1 vector? It's just U1. And so in this case, it's just the number 1. And then I want to find V2. Well, I'm supposed to take my second U value and subtract the projection of U2 onto V1. And then we can write out what that means. It was U2 dot V1. But here we're not doing a dot product. We're doing the more general inner product. So inner product U2 V1 divided by, well, before it was V1 dot V1. Now we're just replacing dot with a more general inner product, V1 inner product V1, times the vector V1. And then we just chug out this calculation. We'll get U2, which is X, minus the inner product of U2 and V1. These should be vector symbols overall. Here's my vectors. That inner product here is going to be the integral from 0 to 1 of U2, that's X, and V1, which was the number 1. So that's what that inner product is. That's what U2 dot V1 means with this kind of inner product. And then I have the inner product of V1, V1. Well, that is just the integral from 0 to 1 of 1 times 1 dx times V1. And V1 we said was 1. Once again, we just chug this thing out. I have X minus the integral of X from 0 to 1. Well, let's see. If I integrate this thing, I'm going to get X squared over 2 from 0 to 1. And the denominator, the integral from 0 to 1 of 1 is just 1. So I'll have this. And this simplifies to X minus, the numerator is 1/2. 1/2 divided by 1 is just 1/2. And so this becomes my V2 vector. This is the second basis vector for my new basis. So I'm generating my V1 set of orthogonal bases. So far I have 1. And my next one is X minus 1/2. And I would go on to generate V3 the same way I generated V3 before. It would be U3 minus the projection of U3 onto V1 plus the projection onto V2. And I would just calculate those inner products using this definition. And the result would be a basis. And the next term would probably have X squared plus some junk minus some junk over there. And so I would have 3 vectors, right? These are each 3 secondary polynomials. They span the space, because as long as there's an X squared term and an X squared and a constant term, I should be able to add or subtract and get any secondary polynomial. But not only that, but they'll be orthogonal. If I were to integrate this product from 0 to 1, I would get 0. If I were to integrate this product from 0 to 1, I would get 0. So they're orthogonal in some sense. Okay. Any questions about that? Now, this will generate an orthogonal basis, and it might not be clear what we're going to use that basis for this case. But the other idea of projection was to find out, the idea of closeness. So now I can really do that projection. I can find that projection vector just using this definition of the inner product. All right. So that's kind of a generalized example. Now I'm open for questions. Any questions from homeworks or from that final exam template, or any lingering questions from eigenvectors, or any questions from the exam? Question number 5. You know what the question is offhand, or let's find it real quick. All right, so the one due tonight is 6-3. And which one? 5. Okay. Find the distance from Y to the plane in R3 spanned by U1 and U2. So they want the distance from Y to this other plane. Let's sketch out how we... So are you looking for how to kind of start this problem or some of the actual calculation in it? Okay. I would say if I had to guess, if we're doing the right process, there's probably a sign there somewhere along the way. So let's talk about how we would do it. I have vectors U1, U2, and I have some Y. I'm trying to find the distance from Y to the plane that's spanned by U1 and U2. So in other words, if I take any linear combination of Y1 and Y2, I'm generating a plane here. It's kind of this plane that might lie something like this. Okay, that's the linear combination of U1 and U2. That's the span of U1 and U2. Now, what I want to find is the distance. Let me redraw Y1 to make it a little cleaner. I want to find the distance from Y to this plane. Well, to find that distance, I need to project Y down onto the plane. So let's say I project Y onto the plane. I'll get a projection vector. And this vector, Y minus the projection, that will give me this vector. And the magnitude of that vector is what they're looking for. It's what we call the distance from Y to the plane. That makes sense? Okay, now to calculate that, we'll do, to find this vector, it's essentially like finding the third vector on an orthogonal basis, is what it's going to amount to. So we really have to go through that Graham-Schmidt-like process. So we have to, because we can't just say, it'd be nice if we could say it would be Y minus the projection of Y onto U1 plus the projection of Y onto U2. Well, we can't do that. It looks like we should be able to do that. It doesn't quite work like that. Why not? The reason is I can't just project onto any basis for this plane. I have to project onto an orthogonal basis for this plane. So even though these two vectors are a basis for this plane, I got to make sure they're orthogonal basis. Now we could look and see if they gave us an orthogonal basis. It's possible. Let's see, U1 and U2. Look at that, they did. Right, if I have U1 and U2, and I take their dot product, I get positive 6, negative 10, and positive 4. So when I add them up, I'm going to get 0. So they kind of made that nice for us. They gave us an orthogonal basis. So now I really can project Y onto U1 plus just Y onto U2. Okay? But in general, I have to make sure I have that orthogonal basis. Questions about that? All right, so because they were nice, I can really just do this calculation to find the vector, and then it should be the magnitude of the vector, which should be the distance. So one thing to be careful about is distributing that negative sign. That's probably a spot. Does this sound like what you did, or? Okay. Like if you went through this process, still got it wrong, I'm happy to go through it the rest of the way. Okay. Other questions? Who's happy with their exam? Understands all the issues there? All right. Okay, so now we're going to talk quickly about orthogonal matrices. I say let U be I'm going to slide this over here first to be a n by n matrix. N by n, this is a square matrix with orthonormal columns. Orthonormal columns. Not only orthogonal, but they're also orthonormal columns. What does that mean? What am I telling you when I say that these columns are orthonormal? Somebody new here. So, yep, they're vectors of length 1. Absolutely, that's the normal part. What about the ortho part? So they all have length of 1. And what else? What happens if I were to take U2 dotted with U3? It should be 0 because they're also orthogonal. They're orthogonal and they all have length of 1. Okay. So this is kind of a special matrix. This is one we might have constructed for specific reasons. So if this is U, okay, then U transpose is what? Well, U transpose just takes rows and makes them columns. So I would have this is my row, and this is my row, and this is my row. Dot, 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 UN is my row. And then if I looked at this, oops, U transpose, let's see, let's do it this way. U times U transpose, that would be, let's do it the other way. U transpose U I would be multiplying these two matrices, and these are both matrices here because I'm looking at their columns and rows as vectors here. Well, when I do that multiplication, what does that multiplication look like? If I took A, B, C, and D, and I multiplied it by x1, x2, and I did that multiplication, that first entry here would be A times x1 plus B times x2. Then I would have C times x1 plus D times x2. But this thing here, that first entry, is really just the vector, this row, the first row here, dotted with my x vector. It's just doing a dot product. It's doing the dot product of this column and this row. That dot product is going to give me this thing. That's what I do when I do this multiplication. So over here, I can think about it that way. I can say doing this multiplication is really like doing this dot product, this dot product, this dot product, this dot product, all the way down, and that's the first column of my matrix. The second column of my matrix would be this dot product, this dot product, this dot product, all the way down. That's another way we can think of this matrix multiplication. So when I do that, I'm generating this matrix. Well, this would be U1 dot U1, then U1 dot U2, then U1 dot U3, so U1 dot U3, so on and so forth, U1 dot UN. The next column would be U2 dot U1, U2 dot U3, or 2, U2 dot U3, dot, 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 and then dot, 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 all the way along. This last corner would be UN dot UN. But now when I look at that, these are orthonormal vectors. So what is U1 dot U2? What's U1 dot U3? U1 dot UN. All 0 except for this one. What's U1 dot U1? Absolutely. U1 dot U1 should be, let's see, we know that the magnitude of U is equal to the square root of U1 dot U1. So that dot product is equal to the magnitude squared. But these are orthonormal vectors, so they all have a length of 1. So this dot product is just 1 squared, or 1. So what kind of matrix am I left with? What matrix is this thing? It's identity. It's 1 on the diagonal, 0 everywhere else. Turns out for an n by n matrix, this is also true. So for an n by n matrix, U transpose actually has another name. What is U transpose here? If I can multiply on the left of U to get identity and the right of U to get identity, then this U transpose must actually be what? the inverse. So if you have a matrix with orthonormal columns, and it's an n by n matrix, U transpose is actually the inverse. That's kind of a special property here. Okay. So let me delete this thing because it's not exactly true here. There is a relationship if it's an m by n. It's also kind of a special matrix, but it won't be the inverse. Right? If an m by n matrix doesn't have an inverse, so we know that's not going to work here. But there is a relationship, depending on n and m's, where if you multiply on one side, you'll get identity, but not the other. But if it's an n by n and it has orthonormal columns, then U transpose is equal to U inverse. And we say that U is an orthogonal matrix. So a matrix where we have U transpose is equal to the inverse, that's called an orthogonal matrix. And not only is that we have that property where the transpose is equal to the inverse, we have a couple other properties as well. We have these three big properties for these kind of matrices. And we use these properties when we do proofs or when we generalize things to transformations. But they're also important because of what they tell us about the transformation. So this first one says that the length of U times the vector is the same as just the length of the vector. It says we don't change the length of a vector when we do this transformation. This transformation is length preserving. It's a length preserving transformation. And oftentimes we'll want to do that. We'll want to do some sort of transformation where we don't want to mess with the length. So this is a kind of transformation that does that. Now, it's actually pretty easy to prove this one. I'm going to go through this proof real quick here. I'm just trying to show this is true, so I'm just going to start with this side. And say, okay, well, I have a definition for the magnitude of this thing. The magnitude is really equal to the square root of the dot product. So Ux dotted with Ux. Remember, U times X is going to be a vector here. I have a matrix times a vector. I'm going to get this vector result. Now, another way I can write that, though, that dot product, when we define dot product, is to write Ux transpose times Ux. Right, if I take that first one, tip it over on its side, then it's kind of like doing matrix multiplication. But then I have a property of the transpose. If I have the transpose of a product, I can write that as the product of the transposes, but I have to reverse the order. And that was one of our transpose properties. And what does that allow me to do? What's special about the transpose of U if it has orthonormal columns?
Inverse.
It's really the inverse. So this product here is going to give me identity. So all I'm left with here is X transpose X, which is the same thing as writing X dot X. And the square root of X dot X is just the magnitude of X. So this is why we have these different representations for things, because they help us in different proofs. So this is a useful idea. The way the dot product is really the transpose times the vector, that other way to represent it, because it makes certain proofs a lot easier. Let's just think about things in a different way. All right, then we say that if we have the dot product of Ux and Uy, then it's the same thing as just the dot product of X and Y. And that's important also, especially when we pair with this next one. And the proof of this is basically the same too. Just rewrite this as a transpose times something. You'll flip the transpose property just like we did here. You know, the same kind of idea. Now in this it says that, okay, if the dot product of these things is 0, then the dot product of these things is 0. This is also important because just like the first one, whereas the first one said we're not changing the length when we hit it with this transpose, this one says that the orthogonality doesn't change as well. If these things are orthogonal here, they are orthogonal after the transformation as well. So when you transform with a matrix that has orthonormal columns, it is length preserving, and it's also orthogonality preserving. Preserves those two key properties of the vectors. Okay. So those are a lot of special properties from these orthonormal matrices, these orthogonal matrices. Now what's the other thing that we're going to do with them? All right, we're going to use them to do this factorization. So we've kind of already done the hard part. We've already done the Graham-Schmidt process to find an orthogonal basis. And then we could always normalize those when we're done. So these other pieces are just kind of the pieces we're adding on to this. So if we're given a matrix with linearly independent columns, A can be factored as A equals Q times R, where Q is a matrix whose columns form an orthonormal basis for the column space of A. And then R is an upper triangular matrix with positive diagonal entries. Okay. So we're going to factor A into A equals Q times R. Now how do we do this? All we do is take the columns of A, which are going to give us a basis for the column space, and we just change it from that basis to an orthonormal basis. So we do Graham-Schmidt. So the first step is just to use the Graham-Schmidt process to find the orthonormal basis for the column space of A. So you go through that process to find those orthonormal vectors. And you throw those into the columns of Q. So that's how we find Q. Now how do we find R? Well, we're trying to get here. I know what A is, and I've just found the orthonormal vectors to find Q. All I'm going to do is solve for R. So to solve for R, what would I have to do here? Yep, but in fact this time it's easier. Because I know that Q has orthonormal columns, I can just go like this. Because it has orthonormal columns, this is going to be identity. And I'll just use that product to be my R value. That's how I find R. So I use Graham-Schmidt to find Q, and then I take Q transpose A to find R. Okay, so let's finish up kind of the warm-up problem here. So from the warm-up, we have this basis, which I'm going to call the columns of A. We found an orthogonal basis here. And what I want you to do is find a QR factorization for this A, using those columns. So we've kind of already done the hard part. We've done most of the legwork in the warm-up by finding the orthogonal basis. Now what do we have to do to find the QR factorization here? Go ahead and finish the QR factorization. What is Q? Q is the orthonormal basis. Do I just put these right into Q? Are these my columns for Q? Not quite. What do I have to do to them first? I turn them into unit vectors. So the unit vectors of these will be my columns for Q. All right, we're going to start class next time with a quiz. The quiz is going to be the QR factorization for this matrix. Write down that factorization, that matrix A. So you know the question that will be on the quiz right away at class tomorrow. Go through all the details, you can work through it, and we'll just start class with showing the work for that. Any questions before you're looking at this? What's the first vector in my Q? Q is equal to, what is it?
1, 0, 1.
Not 1, 0, 1, 0. I need an orthonormal basis for my columns of Q. If I find the length of 1, 0, 1, 0, it is not 1. So what do I need to do? Divide by the square root of 2. So this should be my first column. Lovely looking vector, right? Now let's go on to the second column. I have to find out the length of this vector, divide that vector by its length to find the unit vector in that direction. These are all orthogonal, but they are not unit vectors. So I have to unit vectorize them, right? I'm pretty sure that's not a word, but. So once I get Q together, then what do? How do I find R? I just take Q transpose times A. All right, hopefully you saw in the final exam template there was a QR factorization. You probably noticed how I wrote it on there as well. There was a problem right before it that said, find the orthogonal basis. Right, do the Gram-Schmidt, because I need to test on that as well. I also need to test on the QR factorization, but I don't want you to have to find another orthogonal basis. It just takes too much time. It's a long process. So you can imagine there might be some other questions like, here is an orthogonal basis, find the QR factorization. So just like I would give you the eigenvalues, eigenvectors of a matrix and tell you to put the P, dP inverse process, I might give you some pieces to make sure you can put them together here instead of having you calculate all the pieces. All right, that's really all the big ideas. We were going to practice for another one. That was the next thing here. After that, I was going to talk real briefly about orthogonal, the closeness idea. So we'll start class with a little quiz, and then we will talk about that probably for about 10 minutes-ish. And after that, it's really going to be a class session of questions from that exam template. So once again, I'm not going to post a key for that template. It's just kind of too big. It's kind of questions I'm going to use on the final, so I don't want to send a key out. But I'm happy to answer any questions from it. Most of the questions you should be able to test yourself, either with your calculator, Mathematica, or some other computation. Like the true and false, I'm happy to answer and kind of discuss. But any other questions as well. So make sure you bring questions. I want it to be a question session. All right, that's all I got for today. Office hours are short today. They'll probably be about a half hour, and then I have to run for the day. If you need anything else, feel free to email me.